distance formula, because we are going to be using it quite a bit today. Square root of x2 minus x1 squared plus y2 minus y1 squared. As a reminder, it comes from Pythagorean theorem. Basically, we want this distance, and what we are doing with the x2 minus x1 and y2 minus y1 is we're checking this distance and this distance. Here's first one I drew is my x distance, second one I drew is my y distance, and we're doing Pythagorean theorem to solve for the distance we're looking for. But that is our distance formula. Make sure you get it written down, because we're going to be using it on these examples that we're about to look at. And what we're starting to look at today is our unit on triangles. So this unit is all about triangles, different types of triangles, showing triangles. We're now showing entire shapes are congruent. All that good stuff is what we're going to see here today. So classifying triangles. This is some more vocab to describe what type of triangles these are. First off, let's start by looking at classifying them by our angles. So we have a few different ways that we can describe the triangles by angles. First off, we have acute triangle. Acute triangle means it's got 3 acute angles. So all 3 of the angles are acute. For a right triangle means that it has a right angle in the triangle. Pretty straightforward. And then obtuse triangle means it's got an obtuse angle, an angle bigger than 90 happening in the triangle. And then equiangular triangle. That's a tricky one to wrap around saying the word, but it does exactly what it says. Equiangular, all the angles are equal. So that is the different types of triangles. And the important thing to keep in mind about the angles in a triangle, and we're going to use this over and over again throughout this chapter, is that in a triangle, the angles have to add to 180 degrees. We'll actually talk about and show why that has to be true later on. But the angles in a triangle have to add to 180 degrees. It's just a fact about triangle, any of these types of triangles we're talking about, angles have to add to 180. So that's why, if you look at right triangle, how many right angles does it say it has? Just 1, right? So the reason that is because if we got 3 things that need to add to 180, if one of them is 90, I got 2 angles, and I need those other 2 angles to add to 90. So I have to have the other 2 angles be less than 90. I can't have 2 right angles in a triangle because that's 90 and 90. That's already 180, and then I have nowhere to go for the third angle. Same thing with obtuse. If it's obtuse, then that angle is bigger than 90. I can't have 2 angles bigger than 90, because if I have an angle bigger than 90 and an angle bigger than 90 and add them together, that's bigger than 180. And then my question that I'll leave you with without an answer is equiangular triangle. Since the angles add to 180, then you should know, if all the angles are the same, what each angle has to be. I'll leave that for you to ponder. There's only one choice of number that they could be. All right, by the sides. So now we're talking about the sides, the segments, as opposed to the angles of the triangle. So these are 3 different words, probably in, I'll go in order of most familiar to least familiar. On the right here, we have equilateral. In an equilateral triangle, again, lateral sides and equal. So equal sides. All the sides are the same. And then we have isosceles. 2 of the sides are the same, and the third one is not. And then scalene, that's probably the one you're least familiar with. Scalene means that none of the 3 sides are the same. So it's how many of the sides are the same that we're looking at. So we're actually going to use these vocab terms here to figure out whether, what type of triangle it is by the fact of whether the sides are the same. And the way we can determine whether the sides are the same, when we say the sides being the same, guess what we're talking about? We're talking about the length, the distance. Here's where our distance formula comes in. So that's what you're going to see here today. We're going to use the distance formula to classify PQO by its sides. So in order to do that, all we're going to do is we're going to use the distance formula. And what we're looking for is how many of the sides are the same. So we're doing these distance formulas, and we're keeping track of how many matches we have. So don't forget that we're looking for, on these problems, how many sides are the same. Okay? That's the big picture of what you're looking for. Don't forget that, because we're going to be in the weeds of the distance formula, and the distance formula can get pretty complicated. And so we're going to spend a lot of time chugging through the formulas, but don't forget that what we're looking for when we get those final answers is, are any of them the same? So we're going to start with P to Q, and then we will have Q to O, and then we will have P to O. So we're going to have 3 distances, and within those 3 distances, we're seeing whether we have any matches. That's what we're looking for. So for P to Q, here we go. I won't rewrite the distance formula because you already wrote it down. But let's take a look. This is the structure of the formula. X distance squared plus the Y distance squared, all under a square root. Here we go. We have Q and P, so we're going to start with our X coordinate. X coordinate of Q is 6, minus our X coordinate of P is -1 squared. Plus, we have our Y coordinate of Q is 3. The Y coordinate of P is 2. We're going to subtract them squared. So we subtract the X coordinate squared plus subtract the Y coordinate squared. Square root. 6 minus a -1 is 6 plus 1 is 7 squared, plus 3 minus 2, that's 1 squared. So let's square those. 7 squared is 49, and then 1 squared is 1, and 49 and 1 is 50, all under a square root. Oh, hey, you might remember that can be simplified. Let's do that real quick. We talked through how to simplify a square root. We divide by the smallest number we can, which is 2. And we look, can we still divide by 2 anymore? No, we can't divide by 2 anymore, but we can divide by what? 5. And we get 5. Can we still divide by 5? Yeah, we can still divide by 5, and we get 1, top of our tower. And remember that when you do this, you're looking for pairs. We have a pair of 5s that can come out of the square root, and then we have a 2 by itself that stays in the square root. So 5 square root of 2 is our distance. Now, after each of these formulas, I'm going to remind you that we're looking for matches. And we see that we don't have any matches yet because, well, we only have one side. So let's do the next one. Q to O. All right, this is going to be a little easier because one of the coordinates is 0, 0. So I'm going to go a little faster this time. X distance. So our X coordinates are 6 and 0. We're going to subtract them squared. 6 here and 0 here. Plus the Y coordinates here are 3 and 0. We're going to subtract them squared. So 3 minus 0 all squared. That will give me 6 minus 0 is 6 squared. That's 36. 3 minus 0 is 3 squared is 9, and that's 45. All under square root. Hey, that can be simplified too. We can't divide by 2 this time. What can we divide by? 3. We can divide by 3. And if we divide that by 3, we get 15. Can we still divide by 3? Yeah, we can still divide by 3. And we get 5. Can we still divide by 3? No, we can't divide by 3. We can divide by 5. So we got a pair of 3's that can come out of the square root and a 5 by itself that can stay in the square root. So we got 3 square root of 5. All right, now, key question here. The key question here, do we have a match? No, we don't. Right? Because we have 3 square root of 5, we have 5 square root of 2, or we have square root of 50 and square root of 45. Guess what? Not the same. So these two sides are not congruent. They're not the same. So we do not have a match. But let's look at our distance from P to O and see if we have a match. So again, we're going to start with our X coordinates. The X coordinate of P, -1, minus the X coordinate of O, 0 squared, plus. We're going to look at our Y coordinates. Y coordinate of P is 2, and the Y coordinate of O is 0. We're going to subtract them squared. All right, now this one's going to be quicker. -1 minus 0 is -1 squared, and then 2 minus 0 is 2 squared. Now, don't forget, I will point this out, don't forget that -1 squared, I should never square a number and wind up with a negative, right? -1 squared should be -1 times -1 is a +1. So make sure that all these answers are positive because you should not get a negative distance. If you're getting a negative under here, then something happened because distances are never negative. So we have 1 plus 4, that's 5. Don't forget it's still under square root. So we have square root of 5. And so now we ask again, do we have a match? No, we don't. No, we don't. So, therefore, we have none of the sides the same. So none of the sides are the same, and we had a word for when none of the sides were the same. Back here, which one had none of the sides the same? It was scalene. So we're going to say that this is a scalene triangle. So again, to talk through that again, we're doing out all the distance formulas. We're seeing if we have any matches. We're keeping track of how many sides measure the same. And we're using that to determine where these go. All right, so let's look at another one. And this one I want you to see if you can do it on your own. I am making a change to one of the coordinates here. C it says is 7, 1. I would like for you to change that and make it 7, 8. So make that coordinate 7, 8. And I would like for you to try these. So work out your distances, work out the distance from A to B, distance from B to C, distance from A to C, and keep track of whether you have any matches. I'll pause here for about 2 to 3 minutes. Notice on the graph, that graph counts by 2's so that you can graph all 3 of those points. Also, don't forget, one thing I see fairly often on these problems is that people will forget the square root. So don't forget the square root as you're trying these and working through these. Keep that square root until the end of the formula, until you get your final answer, all the way through. Again, you should have 3 distances written out because we have 3 sides that we're checking. And we're going to look to see how many of those distances are the same as each other. I'll put that distance formula up one more time in case you need to go back and write it down. One more minute. Again, don't forget I made that change for point C. Instead of 7, 1, it should be 7, 8. Because that's going to change where the triangle is, what it looks like, and what our distances turn out to be. Again, don't forget the square root stays through the whole thing. Don't lose your square root partway through when you do these formulas. All right, here we go. One thing you're going to see on this first formula is your negatives. So we've got x coordinate of A is 6 minus x coordinate, x coordinate of B is 6 minus x coordinate of A is 2 squared. X coordinate of B is -1 minus x coordinate of A is 4 squared. Now, when you do that, you're going to have -1 minus 4 is -5. When I square that -5, remember that's going to be a positive because I have -5 times a -5 is a positive 25. Those should always be positive. So we get 16 and 25. That's 41 underneath that square root. So that's A to B. That's square root of 41. We're going to keep that in our back pocket here and then go on to B to C. Now, B to C, thing to point out here is we have 8 minus a -1, so that turns out to be yes, 8 minus a -1, that turns out to be a positive 9 squared. So that'll be square root of 82. So far we have square root of 41 and square root of 82. Do we have a match yet? Nope, not yet. But we still have one more distance to go. For A to C, let me go across here. For A to C, we have square root of 7 minus 2. That's x coordinates of C, x coordinate of A, squared. And then we have 8 minus 4, y coordinate of C, y coordinate of A, squared. 7 minus 2 is 5. 8 minus 4 is 4, squared. +25 plus 16 square root of 41. And now we look and we see, again, big picture, so that we don't get lost in the weeds of the formulas. Big picture is, do we have a match? Give me thumbs up or thumbs down. Do we have a match? Yes, we do. We do. We have square root of 41, square root of 41. So how many, hold up number of fingers, how many sides are the same? 2 of them. And so, what was our name for 2 of the sides being the same? It was isosceles. So we're going to say that that triangle is an isosceles triangle because 2 of those sides were the same, but the third was not. And I have color-coded up on the graph A to B and A to C, and you'll notice that they've got the tick marks because they're congruent, because they're the same distance. By definition, it's what congruent means. So 2 of the sides were the same. That makes it isosceles. So that's big picture what we're doing there. We're doing our distance formulas. We're keeping track of how many of those sides are the same. All right, going on. Congruence. So let me clear off everything here. If two figures are congruent, so this isn't talking about entire shapes. So far we've just talked about individual measurements, like a pair of sides, a pair of angles. Here, if two shapes are congruent, same size, same shape. What will determine same size is all of the sides being the same, and what will determine same shape is all the angles being the same. So that means all these different measurements, all the different sides and all the different angles in the shape are the same. If that happens, then the entire shape is congruent. Entire shape is congruent. So in order for that to happen, we need to check that all of the sides and all of the angles are the same. And remember that when we talked about those transformations, we said that those different transformations created congruent shapes. So for example, this shape over to this shape, you'll notice, is a translation. Because it's just taking A, B, and C and shifting it over to the right creates the other shapes. So now we have congruent statement. A congruent statement, this is an important term here. Congruent statement is a statement that lists corresponding vertices in the same order of the two congruent polygons. So it is showing what pieces are congruent to what. So because of that, order matters when we write these congruent statements. Order matters. Order is important when we write these. So in this example, the idea when we write these is that you can write the first shape in any order, and then you need to match it in the second shape. So it does not matter what order I choose for the first shape, but the second shape has to match it. It's locked in to be a certain order. So for example, if I choose to make this triangle A, then B, then C. All right, you're seeing me write triangle ABC. So remember how with angle we wrote a little angle there before the three letters? Well, when it's a triangle, we put a little triangle before the three letters. All right, so I can choose whatever order I want. ABC, BAC, CAB, CBA, any of those orders is fine. But once you choose an order for the first one, you need to match it in the second one. So because I chose A, B, C as my order, then I'm going to look and see, because I chose A first, I need to match it for what comes first in the other shape. So angle A, what did angle A match up with? Well, it matched up with angle F. So I'm going to put F first. Or you can think about it in the transformation. So because B goes second, I need to match it up with what goes second in the other one. So B, if I shift it over with the translation, shifts over to E. So E is going to go second there. And because C goes last, D is going to go last. Notice it's not necessarily alphabetical, but that order matters because this will be a powerful statement. It will show exactly what sides are matching up and exactly what angles are matching up. But in order to do that, you need to write it in the correct order. So that's what you'll see on these problems. So as I said, all the sides need to be the same, all the angles need to be the same. So let's take a look at what that looks like. First off, describe the transformation that maps one triangle to the next. So if I look at these two triangles, remember with our transformations that we looked at in the last chapter, we had translation, which was shifting. We had reflection, which was flipping, and rotation, which was turning. So for one of the triangles to get to the other triangle, the type of transformation happening this time is what? Translation, rotation, or reflection. Well, if I take a look at where the points are going, so let's, for example, look at L. Where is L going? Well, L is going over to R, right? Because that's where the two tick marks are. So watch up here closely. If L is moving to R because of that group of tick marks, it cannot be a reflection because a reflection would flip it and send it down to L down to around where T is. But it's not doing that. It's moving up to R. So that means it must be turning. It must be a rotation. All right, and that's one question I'll ask about these shapes is what kind of transformation are we looking at? Because if they're congruent, there must be some transformation going on that can bring one of the triangles to the other. So now we're going to identify all pairs of congruent corresponding parts. I'm going to start with my sides. And luckily, everything has tick marks laid out for us. So we can just look at those pairs of tick marks, look for those pairs of tick marks and see what is matching up with what. I should have 3 pairs of sides matching up and 3 pairs of angles matching up. So first off, for the sides, we have J to K being congruent to, well, J to K is matching up, 1 tick mark matches up with 1 tick mark, T to S. That's pair of sides number 1. And I'm just going by the tick marks. So J to K matches up with T to S. Then our next pair of sides, we're looking for the 2 tick marks. We have K to L. In K to L, we're then looking up for what matches up with the 2 tick marks over here. Well, K to L matches up with S to R. That's the one that has 2 tick marks in the other triangle. And then finally, that leaves J to L matching up with T to R. So those are the 3 pairs of sides that match up and have to be congruent. So there's my 3 pairs of sides. Then we're going to look at our 3 pairs of angles. So angles, what pairs of angles have to be the same? Well, again, we're going to go by the tick marks. So I have angle K. Angle K has 1 tick mark. I'm going to match it up with the other one that has 1 tick mark, which is angle S. Then we had angle L, congruent to. Well, where did R go? Or where did L go? It went up to angle R. So angle L rotated up to angle R. And finally, we have angle J. Angle J, it's got 3 tick marks. J matches up with the 3 tick marks over here, angle T. So as I said, we have 3 pairs of sides and 3 pairs of angles that we're matching up with each other here. 3 pairs of sides and 3 pairs of angles. And that's what it needs to make the triangles congruent. All 3 pairs of sides and all 3 pairs of angles need to be the same. So then, we're going to write a congruent statement. I'm going to start with that triangle symbol to say, hey, we're talking about a triangle, not an angle. And I'll pick an order for the first one. J, K, L. I'll just pick that order. And the idea is that once I pick that order, my order for the second one is locked in. It has to go in the correct order for the second one. If I pick any other order other than the one I'm about to pick, it's not correct. So J, K, L, the easiest way is to look at the angles. What did I match J up with? T. So because J went first, T is going to go first. Because K went second, what's going to go second? S. And because L went last, guess what? R is going to go last. So triangle JKL is congruent to triangle TSR. Now, the power behind this statement is it shows me all 6 of these statements wrapped up into one statement. When you see that congruent statement here, it will tell me all 3 of these different statements hidden in it. So for example, if I know, for example, angle K matches up with angle S because K is the second letter, S is the second letter. So obviously all the angles matched up, but also we can see the sides matching up. For example, J to K. What does J to K match up with? Well, J to K are the first 2 letters. So J to K is going to match up with the first 2 letters over here, which is T to S. J to K, first 2 letters matches up with first 2 letters, T to S. And that is this statement happening right here. So you can read it from that congruent statement, but that only works if you put the statement in the correct order. Because if you put it in the wrong order, then these sides and angles won't match up the way they're supposed to. So that's why the order matters and it's important. It takes all 6 of these statements and puts it into a single statement where you can automatically read, here are all my sides and here are all my angles that are the same by matching them up. So we'll look at using that next time.